Welcome back to the Deep Dive. Today we are diving into a topic that, on the surface, seems completely fundamental. But it turns out to be anything but simple.
That's right.
We're talking about the very dirt beneath our feet.
Mm-hmm.
And more specifically, probably the most classic measurement in all of agriculture soil pH.
And this deep dive is, well, it's a bit unusual. It's actually rooted in a moment of real academic curiosity. We're sort of stepping into a classroom.
Right.
Professor Hendricks' Nature and Innovation class, to be exact. And two of his students, Kesser and Steen, have, they've basically hit a conceptual wall.
A wall between what they're reading and what they're seeing.
Precisely. They've been studying the standard textbooks, the ones that preach the gospel of soil chemistry, but their own work, their own field work with soil microbes has shown them a glaring conflict.
Exactly. And that's the core tension, the conflict that really drives this whole deep dive. It's this traditional sources, the big foundational texts, they all insist that the overall soil pH is the master variable.
The one crucial factor.
The one factor that dictates whether essential nutrients are available or if they're, locked up. It's the master key that unlocks the mineral pantry.
But Kesser and Steen are asking this really disruptive question.
Is this whole understanding, this singular focus on chemistry, is it just fundamentally incomplete?
They're essentially asking if that one single average number you get from a bulk soil test, that average pH reading, is even relevant.
Compared to what's actually happening on the ground.
Compared to the intense, dynamic, local action happening right at the root tip, an action that is almost purely biological. Is the local negotiation by the plant and the soil life actually more important than, say, the statewide weather forecast?
So our mission today is to unpack their sources, their whole conversation, and to really question this reliance on simple static chemical measurements. We want to explore the complex, dynamic, and intensely living nature of that root environment. We're going way beyond the textbook.
It's the ultimate investigation into whether our modern management practices are just oversimplifying a living system.
Okay, so let's unpack this. When you go to the hardware store and you buy a bag of agricultural lime, the advice on that bag suggests this massive universal fix based on that simple pH number. We really need to explore whether that advice is based on an idea that is frankly just not telling the whole story. So we have to start with the textbook mandate. This is the knowledge base that Kesser and Steen really had to challenge. For decades, standard agriculture, horticulture, biology. They've all emphasized that pH is this master variable. And to be fair, for a good reason, right?
Oh, absolutely.
Yeah.
The rationale is completely clear and it's chemically sound. Soil pH, which is just a measure of hydrogen ion concentration, it controls the solubility of essential nutrients and therefore their availability.
So we're talking about minerals like calcium, magnesium, iron.
All of them. They might be physically present in the soil, locked inside clay structures or mineral particles, but if the pH is too high, many of those elements like iron or zinc, they become insoluble. They just precipitate out.
And if it's too low?
If the pH is too low, the opposite happens. Elements like aluminum or manganese can become too soluble, and they can actually reach toxic levels for the plant.
It's the ultimate Goldilocks problem, then. The chemical environment has to be just right.
It does. A perfect example is phosphorus. At a low pH, an acidic one, phosphorus binds really tightly with iron and aluminum. It's locked up. At a high pH, an alkaline one, it binds just as tightly with calcium. Locked up again.
So there's this tiny little window of opportunity.
A very narrow window, usually between pH 6 and 7, is considered ideal because it's that sweet spot where most of the essential nutrients are soluble and accessible at the same time. It's one thing to have food in the pantry, but the pH is the key to the can opener.
And this chemical logic, this rationale, it informs the entire structure of modern farming. If you're running a business, a farm, you're relying on precise soil testing to know the exact dose of lime to raise the pH or sulfur to lower it, all to get that optimal, predictable yield.
It's a completely engineered approach. The core assumption is that the soil is basically a chemical volume that needs a precise external adjustment based on a number. And look, this approach has led to tremendous productivity successes.
Right. You look at intensive farming in Western Europe.
Absolutely.
Yeah.
But the underlying philosophy is one of external control and correction.
But this is where the plant, the living, dynamic nature of the plant, just completely upends that passive model. What Kesser and Steen discovered is that the plant it's anything but passive. It doesn't just sit there and wait for the perfect pH. It acts.
And that is the critical counterargument. Plants actively engage with their soil environment through their fine roots, specifically at the root hairs and the root tips. They are not inert vacuum cleaners just sucking up dissolved ions. They are dynamic negotiators.
And the central mechanism for that negotiation is something called ion exchange.
Yes. So let's really delve into the chemistry of that because it's fascinating. If you look really closely at the root surface, the root cells are metabolically active. They respire, they produce carbon dioxide, which dissolves in the soil water, forms carbonic acid, and that releases hydrogen ions, H+.
And the roots can also just pump them out directly.
They can, using metabolic energy, and these H+ ions, they aren't just a chemical byproduct, they are currency.
Okay, a currency. Explain that.
Well, the H+ ion has a positive charge. And the soil particles, so clay and organic matter, what we call humus, they have a very high density of negatively charged sites on their surfaces.
So they're like magnets.
Exactly. They hold on to positively charged nutrient ions, which we call cations. Things like calcium, magnesium, potassium, they hold on to them, preventing them from just washing away with the rain. This whole system is called the cation exchange complex, or CEC.
Okay, so the essential nutrients are stuck to the soil surface. How does the plant get them off?
It deploys its currency. It deploys its H+ ions. The plant releases an H+ right at the root hair, and it forces an exchange. The H+ is small, highly charged, and it pushes the nutrient it wants, let's say a calcium ion, off that negatively charged binding site and into the soil solution where the root can then absorb it.
It's a literal swap meet right there at the microscopic level.
Precisely. And this is the key. This mechanism demonstrates that the plant is locally and strategically altering its own chemical environment. Every time a plant releases an H+ ion, it lowers the pH in that exact, tiny, localized area.
It's creating its own little acidic microenvironment to pry loose the nutrients it needs moment by moment.
That's it. So if the plant needs calcium, it acidifies the immediate root zone to liberate it. If it's absorbing an anion like nitrate, it might release bicarbonate, which actually raises the local pH.
So this shows that pH isn't some static property of the soil.
Yeah.
It's a medium of exchange. It's an active negotiation.
And this activity happens continuously, day and night, as the plant grows and feeds. The plant doesn't wait for the bulk soil pH to be magically perfect. It adjusts its own microenvironment on the fly. And that active management is what modern agriculture, with its focus on bulk numbers, tends to just completely overlook.
And when you realize that, it immediately brings us back to the standard advice you get as a gardener.
Yeah.
It just casts that commercial lime bag in a truly questionable light.
Oh, absolutely. You look at a bag of agricultural lime, which is typically just pulverized calcium carbonate, and the advice is to apply, X pounds per Y square feet to raise the bulk pH.
It treats the entire area, whether it's a backyard or a 1,000-acre field, as one big homogeneous chemical volume that needs this global blunt correction.
But the reality is that no backyard, let alone a commercial field, is homogeneous. You have differences in drainage, you have buried rocks, compacted zones, you have wildly varying amounts of organic matter.
The absurdity is in the scale. Applying lime globally raises the pH across the entire soil profile. It's this enormous, slow, systemic correction designed to make the chemical availability curve, generally favorable.
But the plant, as we just established, might only need a temporary, localized micro-adjustment right at the root tip.
It's like trying to adjust the volume on one person's headphones by turning up the master volume for an entire stadium.
Yes.
You're just overcorrecting a local problem with a blunt macro solution.
And that blunt solution often ignores the metabolic cost to the plant and its efficiency. I mean, if the plant already has the biological machinery to generate the H+ ions it needs to negotiate successfully, why are we spending massive amounts of money and fuel and time hauling and spreading bulk chemicals?
So the textbook view, it sort of promotes this dependency on external inputs.
While the biological view highlights the plant's own inherent capacity for self-regulation.
Which frames that textbook definition pH is static and must be fixed externally as a description of a broken or a simplified system, not a healthy, complex, living one.
And to really understand what Kesser and Steen are getting at, we have to move from that concept of bulk soil chemistry to the concept of the living system. We need a deeper definition of what soil pH even means in a biological context.
Okay.
At its core, pH is really a measure of the effective energy environment right around the roots. It determines the velocity, the direction, and the ease of chemical access. It's not just about what is present, but about the tempo of nutrient cycling.
And that brings us to the really profound limitation of the standard measurement.
Exactly. When a farmer or gardener sends a soil sample to a lab, they are measuring an average value across that entire sample. And
Uh,
critically, it's a snapshot in time.
Yeah.
It might take days for the lab result to come back.
And in that time,
In that time, the actual chemical environment right next to the active root where all the action is, has probably changed hundreds of times.
and this is where it gets really interesting, we have to zoom in, way in
Mhm.
on the rhizosphere. This is the literal life support system for the plant.
The rhizosphere is defined as that narrow region of soil, usually just 1 to 3 millimeters wide, that is directly influenced by root secretions and all the soil microorganisms that are associated with them. This is where the plant lives, it's where it negotiates, it's where it thrives. It is an area of just intense biological and chemical activity.
And the chemical environment there is radically different from the bulk soil measurement you get from the lab.
Oh, markedly so. Studies have shown that the pH in the rhizosphere can fluctuate dramatically. Sometimes a full pH unit higher or lower than the bulk measurement taken just a centimeter away.
A full pH unit, that's a huge difference.
It's massive, and this difference is powered by those root exudates we talked about, the H+ ions to lower pH, organic acids to chelate, and also just a massive influx of carbon compounds.
So let's talk about that plant negotiation again, but now through the lens of the rhizosphere. When the root secretes H+, it locally lowers the pH, and that frees up locked nutrients.
Think of it like a localized acid bath. That momentary drop in pH allows the root to dissolve calcium from calcium carbonate, or magnesium from mineral silicates, or, most crucially, phosphorus and trace elements like zinc and copper that might be really tightly bound to iron oxides.
It's resource management at the cellular level.
Yes, using the plant's own energy to manage its local chemical environment.
But that sounds incredibly energy intensive for the plant.
Yeah.
Does the plant always have to do all this heavy lifting itself?
Not always, and this is where the biology just shines. The surrounding microbial community, which is absolutely enormous in the rhizosphere, often assists. Bacteria and fungi are constantly secreting their own low molecular weight organic acids.
Like oxalic acid or citric acid?
Exactly, and these act as powerful chelating agents.
Okay, a chelating agent.
Wow.
It basically grabs a nutrient ion that's locked up and holds it in a soluble form, making it bioavailable no matter what the bulk pH is.
Precisely. They're like chemical bodyguards, keeping the nutrient available until the plant needs it. The microbial community essentially adds this massive layer of adaptive capacity to the whole system.
And this brings us to a critical concept that Kesser and Steen emphasized with Professor Hendricks, the biological buffer.
Yes.
So explain the biological buffer. How is that different from a simple chemical buffer system like the carbonate system we see in the ocean?
That's a great question. A chemical buffer provides stability through a predictable equilibrium. A biological buffer provides stability through adaptive flexibility and, importantly, physical structure.
Okay.
So soil with high biological activity, lots of fungi, bacteria, dense organic matter, it can handle far greater swings in pH without losing its core function, which is the reliable delivery of nutrients and water.
So what are the biological components actually doing?
Well, first, physical transport. Fungal networks mycelia can reach far, far beyond the root tip. They can transport nutrient ions over distances, completely bypassing localized areas where the chemistry has locked up, say, all the phosphorus.
So they're like a subway system for nutrients.
A perfect analogy. Second, there's structural sequestration. Microbes stabilize carbon structures, and those organic compounds, like humic acids, have thousands of negative binding sites. This significantly increases the soil's CEC, its storage capacity.
So if the soil is rich in life, it has a higher storage capacity and more diverse ways of delivering nutrients. It can buffer the system against extreme chemical shifts.
That is the key takeaway. In a living system, flexibility and adaptation are the rules. The microbial community can dissolve phosphorus at a bulk pH, where a pure chemistry textbook says it should be completely inaccessible.
Ow.
Because they're creating a microscopic chelated environment right around their own hyphae that just overrides the bulk condition.
This really makes the pH reading less of a target you have to control and more of a symptom of the system's overall health.
Exactly. If the bulk soil pH is, for instance, a bit low, but the soil has high biological activity, the plants might be absolutely thriving.
Because the microbes are handling all the local adjustments efficiently.
That's it. A farmer managing a purely chemical system sees low pH as a crisis that requires immediate massive liming. But a regenerative practitioner who's thinking along the same lines as Kesser and Steen sees that low pH is just an observation. They look at the biological activity.
Sure.
Are the plants healthy? If so, the system is buffered and adaptive, and that single pH number is actually misleading.
This realization that pH is a dynamic secondary factor in a healthy system, it forces us to challenge one of the biggest assumptions of modern agricultural science, that the control of pH is the foundation of fertility. And this means we should probably shift our perspective to history.
It's a crucial exercise. We have to remember that sophisticated agriculture existed for millennia before the Danish scientist Søren Sørensen invented the pH scale in 1909.
Right. Farmers were highly successful for centuries without a pH meter.
They weren't operating without knowledge. Their knowledge was it was qualitative, not quantitative.
Okay, so this old wisdom, what was it based on?
It was based on intense, centuries-long observation of performance, of behavior, and of stability, rather than relying on a single number. A farmer knew their land by how water behaved, how quickly the soil soaked up rain, how fast it dried out, whether it cracked when it was parched.
They were reading the land itself.
And they knew which native plants, specific weeds or wild legumes thrived there. Those plants signaled specific mineral profiles. The indicator was always the living outcome, not the chemical input. They were effectively reading the land's biological capacity.
And they selected their crops based on that reading.
They did. They didn't choose the variety that would produce the highest theoretical yield if you maximized all the inputs. Instead, they chose varieties that were optimized for stability in their specific landscape.
So varieties that could handle the local variations in drainage or sunlight or the natural pH range.
Exactly. This might have meant lower peak yields, perhaps, but it dramatically reduced their dependence on constant external corrections like liming or fertilizing.
That sounds like a much more resilient form of agriculture.
It is, because it prioritizes resilience over brute force output. It was a partnership with the land's capacity, whereas modern, input-driven agriculture often demands that the land conforms to the crop's genetic maximum potential.
Which requires constant external management to enforce that compliance.
Right.
Now, let's be fair and acknowledge the undeniable successes of that modern system. Places like Holland and Denmark have achieved just mind-boggling yields by managing water, nutrients, and pH with extreme precision. It absolutely works if your goal is maximum yield per hectare.
It works, but it absolutely relies on that fundamental assumption that the soil is a chemical matrix that must be stabilized and optimized from the outside. The system requires constant monitoring and correction, which is, metabolically expensive at the system level, though highly productive for the crop.
Which brings us to Professor Hendricks' favorite weapon against this assumption, the old Swedish cabbage study. It seems to directly undermine the idea of a single required optimal pH.
It's a fantastic teaching tool because it just defies textbook predictions. The study demonstrated an increased yield of cabbage, a crop that is famously sensitive to pH, at significantly lower pH levels than what was traditionally stipulated as optimal.
So if the textbook says cabbage needs a pH of 6.5 to access calcium and prevent clubroot disease, and the study showed better growth at, say, 5.5, the conventional wisdom failed dramatically. Why?
And that raises the important question. It means that biological systems do not always adhere to simple, theoretical chemical solubility curves. The expected chemical constraints must have been overridden by something else within the living system.
So we have to speculate on the mechanisms. What are the primary biological drivers that could let a plant succeed despite a chemically suboptimal bulk pH?
One major candidate is fungal dominance. A lower, slightly more acidic pH often favors specific fungal species, including beneficial mycorrhizal fungi. And these fungi are exceptional at nutrient scavenging and transport.
So they can reach phosphate ions that are locked up in iron complexes, chelate them, and then transport them directly to the root,
effectively nullifying the chemical lockup that the bulk pH reading would predict.
The fungi are performing the extraction and delivery service that the plant couldn't manage on its own at that pH level.
Exactly. Another factor might involve the management of aluminum toxicity. Low pH often solubilizes aluminum, which is toxic to roots. However, high organic matter content, which can be stimulated by a low pH favoring fungi, provides binding sites for that aluminum. It effectively detoxifies the soil locally and allows root growth to continue unimpeded.
And what about disease suppression? Maybe the pH level is wrong for optimal nutrient availability, but it's right for suppressing a key soil-borne pathogen.
That's entirely plausible. Soil ecology is highly competitive. If the lower pH stimulated beneficial organisms that aggressively suppressed a key disease, which is a major issue for cabbage, the overall improvement in plant health would easily override any minor chemical constraints.
It validates the farmer who knew their land grew phenomenal cabbage,
Ye-
even if the university soil test came back saying correction required. The system was stable and productive, even if it was chemically anomalous.
It confirms that in a truly living system, chemistry, biology, and structure are inseparable. The old farmers observed systemic stability. Modern science tries to control every variable, but sometimes misses the underlying complexity and resilience that's provided by the life within the soil. The goal shouldn't be perfect pH. It should be robust, adaptive biology.
So let's shift now from the variable of pH to the actual architecture of the living soil system. We need to look at the central relationship that enables all this resilience: carbon and calcium. The sources highlight that carbon is far more than just general food. It is currency.
This economic analogy is absolutely vital. When a plant photosynthesizes, it's converting sunlight into sugars, and it's estimated that up to 40% of those sugars, those complex carbon compounds, sometimes called liquid carbon, are actively pumped out through the roots into the soil as exudates.
40%. That is an astonishing metabolic investment. Why are they paying so much?
They are paying for essential services. The microbial community provides these services. The payment, in the form of sugars, organic acids, proteins, it stimulates the microbes, the bacteria, the fungi to operate at peak efficiency.
And in return, the microbes do the heavy lifting.
They do. They mineralize nutrients, they protect the roots from pathogens, and critically, they make the soil chemically and physically larger for the plant. They extend access far beyond what the roots could ever reach alone.
So when Kesser and Steen are focusing on making their rich, homemade compost, they're basically creating initial startup capital.
Absolutely. Compost delivers not just the raw materials of fertility, but the relationships needed for a functional economy. It introduces a diverse consortium of microorganisms. You have fast-acting bacteria, you have slow, collaborative fungi. This diversity ensures flexibility. When conditions change, a drought, a shift in pH, a different segment of that microbial economy steps up to solve the problem.
And once that biological economy is thriving on carbon, calcium K2+ steps in as the essential engineer.
The C plus K interaction is the foundation of physical resilience. Calcium, being a divalent reagent with two positive charges, serves as the ultimate bridge builder in the soil. It's the rivet in the steelwork of the soil.
Help us visualize that. What does that bridging action look like at the microscopic level?
We've established that clay particles and humus particles are generally negatively charged. Microorganisms also excrete massive amounts of negatively charged slimes, polysaccharides, and something called glomalin, a sticky glycoprotein produced by mycorrhizal fungi.
Okay.
Calcium, with its two positive charges, can link these negatively charged surfaces together.
So it's physically linking the organic glue, the clay, and the humus.
Precisely. This binding action creates stable soil aggregates. Those are the porous, strong, crumbly structures you find in healthy soil. These aggregates form the structural scaffold of the soil, and that provides the vital macropores necessary for air, for water, and for root penetration.
So without calcium acting as that physical binder, the entire structure just collapses.
Correct. Without sufficient calcium, the carbon structures, the bacterial slimes, the fungi networks, they remain weakly bound. They easily slake or dissolve when water hits them and the aggregates fall apart. This leads to compaction and loss of porosity, and all that valuable sequestered carbon is rapidly consumed and lost as CO2. With calcium, that carbon is bound into the soil structure for much longer.
Which means carbon stabilization, and that means the pH buffering capacity of the system itself remains strong.
Absolutely. And that structural function dramatically influences the dynamic buffer system we discussed earlier. The chemical pH discussion doesn't disappear, it just becomes subordinate to this living architecture.
So the carbonate, bicarbonate, organic acid, CO2, they form a dynamic equilibrium.
A system that resists abrupt, destructive pH swings. This is stability achieved through active movement within boundaries, not stillness. And the biology continues to override the bulk chemistry.
Because the structure is intact.
Yes. When the structural integrity is high, the fungi and bacteria can continue to excrete their organic acids that locally dissolve compounds, calcium, magnesium, iron, even if the bulk pH is technically too high or too low. They are creating millions of microzones of specialized functional chemistry, totally independent of the bulk reading.
So in summary for Kesser and Steen, the advice on the lime bag is insufficient because it treats calcium merely as a pH adjuster.
When in reality,
In reality, calcium is a fundamental structural engineer and a carbon stabilizer. If you manage the carbon by adding organic matter and ensure you have adequate calcium, the system starts to manage its own pH.
that is the ultimate conclusion. When the structural scaffolding is functional, the soil's capacity to handle chemical variation just increases dramatically. It moves from needing external correction to exhibiting this profound adaptive capacity. And now we can look at the really nuanced and clever project that Kesser and Steen are doing, which brings all these concepts together. Their use of fjord water in a sand filter system, inspired by natural farming techniques.
Okay, so Kesser's initial observation was about the nature of seawater. It typically has a slightly alkaline pH, around 8.1 to 8.3, and that's because it's heavily dominated by an active bicarbonate system, right? A continuous balance between CO2, bicarbonate, and carbonate.
A vast natural dynamic buffer system. And in that massive buffer, critical minerals, calcium, magnesium, potassium, are all present in a readily dissolved, ionic, and mobile form. This observation, it's not new to agriculture, it's ancient wisdom.
The use of diluted seawater has a long history, particularly in Asia, and specifically within natural farming systems. The source has mentioned the Jedam tradition. We should probably explain that for the listener.
JDAM, it's from Korea, and it stands for Jeonol Daman Saramdol, which means people who practice natural farming. Its core philosophy is ultra-low-cost farming that maximizes the use of indigenous local resources.
So instead of buying concentrated synthetic fertilizers, they focus on brewing powerful solutions from local materials, weeds, fallen leaves, and in some coastal areas, sea minerals.
The goal isn't high-input fertility. It's the stimulation of indigenous microbial life and providing trace elements in a balanced form. The fjord water fits this philosophy perfectly. It acts as a mineral and a microbe carrier. The focus is on ionic balance and biological stimulation, avoiding those massive brute force inputs.
But we have to address the immediate red flag that comes with ocean water: salinity, salt.
Yes. Ordinary ocean water is problematic for repeated use because of its extremely high concentration of sodium chloride. Sodium ions can displace beneficial ions like calcium from the cation exchange complex, destroying soil structure and leading to compaction and toxicity.
But that's the critical factor that Kesser and Steen accounted for. They're using fjord water.
And because fjords often have significant freshwater input from glaciers or rivers, the salinity is naturally lower. This changes the calculation dramatically. The sodium pressure is reduced to manageable levels, but the critical elements for biological buffering, calcium, magnesium, potassium, carbonate, they're all still highly present. It essentially becomes a liquid mineral solution.
And we should probably emphasize the role of magnesium here.
We should. Magnesium is highly important in that carbonate buffer system and in plant metabolism. It's the central atom in the chlorophyll molecule. And in the fjord water, the balance between calcium and magnesium is often excellent, supporting both structure and enzyme function without the overwhelming toxicity of pure sodium-dominated seawater.
And the microbial life can thrive in this kind of environment.
Indeed. Soil microbes are surprisingly tolerant of mild salinity as long as the sodium doesn't dominate and destroy the structure they need to live in. The calcium and magnesium in the fjord water actively support that structural architecture we just discussed.
Now to the, really, I think, the experimental genius of Kesser and Steen, the sand filter setup. Why use a sand-based system for a complex biological study? Why not just use natural soil?
The sand filter is an incredibly insightful choice because it is a low buffer system. Sand particles are primarily silica, which has almost no cation exchange capacity and very few organic matter binding sites.
Which means there's no reserve store of nutrients and no built-in resilience. It's a naked system.
Precisely. If they were to put this fjord water solution onto natural, highly buffered soil, the soil's own CEC and organic matter would absorb and mask the immediate effects. In the sand filter, all effects, positive or negative, imbalances or successes, are immediate and dramatically visible. The sand filter is effectively a microscope for soil processes.
This forces the plants and the microbes into an immediate active negotiation.
It does. They're creating a clean slate, removing the confounding variables of natural soil's massive buffer capacity. The system must operate through the constant low-intensity circulation of microbes and minerals, relying entirely on root activity, root exudates, and the thin biofilm that forms on the sand grains.
So if the plant successfully negotiates for nutrients, using H+ ions in that sand, Kesser and Steen see the result clearly and quickly. If the system fails, they know immediately that the fjord water didn't provide the right balance for that active negotiation to happen.
They're maximizing the need for that essential microbial and root activity. It makes the underlying mechanisms, the H+ release, the chelation of trace elements, the dynamic local pH shifts, so much easier to observe and quantify than in complex, buckered soil. Their project is advanced because they are focusing on context and connections,
The structure, the life, the balance.
not just chasing a simplistic recipe or a single right pH number.
The conclusion for them is clear then. Their success is rooted in observing how the plant solves the problem, not in solving the problem for the plant.
They've demonstrated the power of curiosity and patience. They're asking the ultimate question of living systems. What can this system figure out if we just give it the right balanced preconditions instead of imposing a chemical correction from the outside?
So what does this all mean? The core takeaway from Kesser and Steen's deep dive is that soil pH is, well, it's a powerful and useful diagnostic tool, but it is deeply incomplete when you isolate it from the architecture of life beneath our feet. It's much more like measuring the weather in a complex microclimate than it is like setting a thermostat.
The required shift in thinking is away from external, prescriptive, chemical input. Instead of asking, what is the soil missing that I have to go add from a bag, we should be asking, what internal capacity does this system have, and how can I support its structural architecture and its biological relationships to help it meet its own needs?
And that focus on architecture, the structural, stabilizing role of carbon and calcium, the microbial economy, the ability of the root to aggressively and locally negotiate for its own nutrients, that's the key to understanding resilient living systems. We're moving from managing simplistic chemistry to supporting complex life.
And that complexity is powerful because it represents inherent resilience. If they maintain that curiosity and patience, the soil itself will continue to teach Kesser and Steen the rest, provided they just ensure there is water, light, and robust biological life active in their system.
A truly profound lesson in ecology and resilience. If this deep dive into the microscopic world of the rhizosphere and the surprising logic of a sand filter has sparked your curiosity and given you a new perspective on the dirt in your own garden, make sure you subscribe to the deep dive for future conversations. We'll continue to explore complex topics and unpack fascinating information one source at a time. We'll catch you next time.